A capacitor is an electric component which comprises of a dielectric material sandwiched between two electrically conducting plates. So it's like that. These two are electrically conducting plates, this one, and a dielectric material inside that, which is an insulator basically. So this is what a capacitor looks like. This is how a capacitor looks like. Now when a DC voltage is applied across a capacitor, say like this, it actually blocks the DC. However, and as a result, charge is stored across this, and when we say it blocks the DC, that means the voltage is, it is as if an open circuit. The applied voltage comes across this, so this voltage will also be V, but there is a process through which it happens, and which is during that process a transient current flows through the capacitor. So the transient current goes something like this. It decays exponentially, and the initial current is basically, if there is an R in the circuit, which there should be, a capacitor is not connected directly, and there will be basically the connecting wires are as well. So the initial current is basically E over R, V over R, because we have used V here. So that is the initial current, and the final current is 0. So then it's blocked, and as a result charge is stored across the capacitor, and as an energy is stored inside the capacitor. So the capacitor acts as a, we can call it as a variable resistance. When DC is applied, initially the resistance is infinity. Initially the resistance is 0, which is, initially it behaves as a short circuit, and when the transient ends it behaves as an open circuit, so the resistance becomes infinity. And the charge stored, or the energy stored, can be said, so capacitor is, the value of capacitor is Q times V, where V is the applied voltage and Q is the charge stored, and the energy stored can be seen like this. So this is basically V dQ, so the amount of V which causes the change in charge, so initially from 0 to certain value. And we can say this, if we integrate it, we can write, instead of what I have written wrong here is, this should be Q is equal to CV, not C is equal. So Q is equal to CV, so C is equal to basically Q over V. That is the definition of capacitor. Charge stored per unit applied, voltage applied. So this one can be written as dQ will be C dV, which is, if we take the C out, this will be V dV, which is half CV square. This is the energy stored, and we can rewrite this in terms of energy stored. That will be Q square over 2C. If we substitute this one here, it will be like that. So that's the energy stored. So basically capacitor is like that, a dielectric material sandwiched between two electrically conducting plates, and it doesn't allow any DC current to flow. However, it allows AC current to flow, and that happens in this way, that when there is an applied AC voltage, let's say with certain frequency, what happens is the voltage keeps changing, the direction keeps changing, once this direction and once that direction, and the transient current, which is like that, and the capacitor voltage, I didn't draw before, is like that. The voltage across the capacitor for a DC applied voltage, that will be like that. So this final voltage will be V, the applied voltage basically, and initial voltage will be 0, because initially it's a short circuit, and after the end of the transient it's an open circuit. So when an AC voltage is applied, the transient current before the transient current for AC can be thought as, if we apply an AC, it is for any instant, it is actually, we can think it as a DC in that instant. So every instant will give rise to a transient current. However, the voltage is changing instantaneously, so the transient current will change also instantaneously, and before it decays there is another voltage that is coming up, so it cannot decay, and this way there will be a transient current, and there will be a continuous current, because the uh, polarity or the applied field basically keeps changing. And what happens is the current actually also takes the shape of the sinusoidal voltage, if it is sinusoidal voltage, and also the energy that is stored in the capacitor, it is alternatively stored and then given back to the circuit when an AC is applied. And so basically it's the same principle, but during when an AC is applied, but the way capacitor acts in a circuit is, though the current origin is the same, for DC it acts as a current blocker, so it acts as an open circuit, while for AC it becomes a sort of a short circuit. No, not probably short circuit, but it gives an impedance which is a little bit more, which we don't want to talk here, but basically it allows the current to flow. We actually can say how much is the it's called reactance. So capacitor reactance is like this, and it is invert of the frequencies. So if frequencies, and this equation is valid for DC as well, if when DC, omega is just angular frequency, so that's 2 pi f. So f is the frequency, which is hertz, and omega is the angular frequency, radian per second. So what happens for DC, omega is 0, as a result xc will be infinite, and as frequency keeps increasing, xc starts decreasing. So that's how capacitor works. With high frequency, with very high frequency, in any circuit analysis with very high frequency, capacitor is thought to be a short circuit, while for DC, of course, it's an open circuit. So basically this is a very small video about capacitor. It works as a energy storage material for DC. For AC as well, it stores and releases the energy. That's how it works with the changing electric field, and the energy stored for DC is given by half CV square, as I mentioned before. So yeah, this is just a brief video about capacitor.